What is it about FloEFD that makes you able to be successful doing CFD even without, let's say, an extensive background in the field? And really the first, the most obvious, is the way that we work with the CAD tool directly on your CAD model, this connection to the CAD that you are probably working in already as an engineer. This is an environment that you're familiar with, and then FloEFD feels like an extension of that already familiar environment. From there, though, if that was all we did, that really wouldn't be enough to make somebody who doesn't do CFD all the time successful, so we need these other enabling technologies. So really the next probably biggest thing is the way we handle the meshing. And in doing CFD, that's oftentimes one of the biggest bottlenecks in the process, is building a mesh and being able to do it quickly and one that will run successfully. And that's where we have an approach that is really robust. It's able to take a really wide range of arbitrary geometries, complex geometries, and mesh them with really minimal inputs from the user, which really gets you through that tedious phase of trying to do a CFD analysis. Next are things like the way we combine regular 3D CFD approaches with these engineering models. And I'm not going to touch on all of the engineering models other than one, which is the way we handle the boundary. And with other CFD approaches, part of the meshing effort that you need to put into building a model is having a representation of the boundary layer with this nice body-fitted type of mesh. And we're able to replace a lot of that with this engineering approach that then enables our mesher with its immersed boundary approach to quickly go through that phase and also still give you a good representation of the boundary layer. So those technologies combined really get you through some of the sort of hardest part of getting a CFD model ready to run. It's an intuitive user experience. We put a lot of focus on ease of use. Again, we know that a lot of our users are not doing this all the time, so they need to be able to feel that they can come back into the software and pick it back up without a long learning curve. And then things like parametric studies, design comparison functionality, lots of things to help you easily be able to run lots of cases, come to an optimized design, compare your designs easily. So with that, rather than talking about these things, I think it's certainly more compelling to go ahead and see it in the software. So let's go ahead and take a look at Solid Edge with our FloEFD add-in. So if you are in Solid Edge with FloEFD, you'll see that, of course, you've got, from our flow analysis tab, you have in the command bar all of our flow-related functions. On the Edge bar, of course, you see as well the FloEFD tree, where you do a lot of managing your project and a lot of your work with respect to setting up a flow problem and running it in Solid Edge. The other thing to note, of course, is you're working directly on the native CAD model. We are going to do, in this case, an analysis of the motor compartment. Let's say that this device, they're concerned about the motor getting too hot, and they want to do some ventilation concepts and just do some thermal management. And so we've gotten rid of the parts that aren't relevant to that, but the ones that are left are all still your native CAD models, and that's what you're going to work with. Quick disclaimer, since this is an actual device, the actual ZoomX, we're not implying that it has any thermal issues, but this is just to show you how our software would work for that type of a problem. So I'll take my lawyer hat back off and get back to doing CFD. The other thing about using FloEFD compared to a classic CFD process is representing the airspace, or whatever fluid space you're going to include in your analysis. And typically in CFD, that is another step that you need to do, is you need to represent that fluid volume as a solid, probably save it out, and identify that this is your solid material or your fluid region. And that's just one more tedious step. Typically, you don't have a solid of that. You have an assembly of the actual device that you're making. So the fluid space is usually just a consequence of the empty regions within it. So we have this nice utility that will isolate that for you. You don't have to actually create that. This tool that you're seeing is just to visualize it. And any changes that you make, you're going to make directly to your CAD model. So that solid or that fluid volume is just sort of along for the ride. So when you make a change to your design, it'll be reflected in that flow space. So from here, a typical way of setting up your first design would be to go through our wizard. Again, we have lots of users who aren't doing this type of work all the time, so they can come back to this, this convenient way of setting up a problem. Kind of gives you a roadmap to walk your way through the setup. You'd assign a project name, pick a unit system. On the analysis type, you would go ahead and say whether it's an internal or external flow problem, and pick some other things that apply to the analysis. In this case, we're going to include heat conduction in solids. So this is going to be a conjugate heat transfer where both the solids are meshed as well as the flow space and get that convection and conduction solution. So as you work your way through the rest of the wizard, you would do things like pick the fluid, in our case it would be air, pick a default solid, and just work your way down through some defaults that help define that initial project that you want to run. Now this morning, in the interest of time, we're just going to finish out of the wizard and get to a case that we've already set up, and I'll just work my way down through sort of the typical things that you would finish setting up to run one of these cases. So really the first branch in the tree there, in the input data portion of your FloEFD tree, is the computational domain. So when the wizard completed, that box that you see would have been around the entire geometry, because we're including conduction, and it assumes that you want to include the solution for all the parts. If you want to just sort of zoom in on that motor compartment and that area of interest, that computational domain has drag handles. You can just easily drag it around your region of interest. And so then just that portion of the model is going to be meshed and solved for, so you don't have to do anything to the rest of the solids itself, chop them down to be just that zoomed in model. You just conveniently drag your computational domain around the area of interest. Working our way down the tree, we would assign some materials to the different parts. In this case, the motor is made of a metal, it's made of steel. Working our way down, we're going to go ahead and assign some flow conditions. What we've done with this, this cover is put in a couple of vents. Initially, it was just a solid cover, but the engineer wants to ventilate this with a fan. So on the left-hand side, we're going to have a pressure condition that lets air just enter into that cavity. And on the right-hand side, we would have a fan that draws air out of the system. So for that, instead of assigning a flow rate, we can go ahead and assign a fan curve and let the flow rate be determined by what the resistance is that the system provides. And of course, there's a database of fans that comes with the software, and you can add your own as well. So those are the inputs that you would do with respect to the flow side. One thing I should mention is that we put lids on those two openings, and they're transparent. That's why you don't see those. And they do two things. They help isolate that internal flow space so it could recognize that blue volume that I showed earlier, and it gives you faces to apply these boundary conditions to. So finishing our way down the tree, next would be assigning a heat source. So that motor is what's putting out the heat in this example. So we can just pick that part either from the graphics area or from your Pathfinder, give it some heat generation rate, and then as we work our way down, we would move to goals. And goals are more about extracting information of interest from the problem. Certainly, when you're doing CFD, one of the things you want to see are the pretty pictures, the flow solution visually, which is hard to get experimentally a lot of times. But there's probably some bottom line numbers that you want as well. And really, in our case, it's probably how hot is that motor getting? So we have a couple goals of average and max temperature for the motor. So we'll be able to quantify that type of information. And then lastly, as we finish going down the tree, would be our global mesh branch. I'll just pull this up just to show you the input that was required for this example. And really all it is using our automatic meshing approach, and just with one global setting, which is that slider bar. That was really all that was required to go ahead and mesh this geometry. And that geometry, if you look at it, is relatively complex. We didn't defeature things. We just left it as the original CAD geometry. As you move that slider bar to the right, that would build you a finer mesh. And the trade-off, of course, is resources and runtime with that. So that is the way that you, at least at the top level, control the meshing. From here, the model is set up, and you'd be ready to run it. You would pull up this run GUI, and you would go through, and if you launch it, it would mesh the geometry and then step into the run and solve it out. In the interest of time today, we are going to just move on to looking at the solution, which of course you're going to do right here in Solid Edge as well. So a lot of the benefits with being in the CAD tool are the way you work with the native CAD model on the setup side, but even the way you look at the results, the post-processing, is nice to be able to see that in the context of your CAD geometry. So I'm going to start with a cut plot. And on it, I am going to show the mesh just because we didn't get a chance to do that part of it live, although this mesh took about 1 to 2 minutes to run on Doug's Surface Pro over here. So what I'm showing is the solution. This is the velocity, so this is the speed of the airflow, and overlaid also with what the mesh looks like through here. And you'll see that both the fluid region as well as the solid volumes are meshed in this one continuous mesh to get this conjugate heat transfer problem. You don't see a solution in the solid part right now because that's velocity that we're looking at. But let's switch over to a parameter that you would see, and this is now temperature. So what we're looking at now is the temperature distribution through this motor compartment, both through the solid as well as in the flow space, overlaid with vectors. So you can see the direction of the flow. So you can see you have the coolest air coming in, through your inlet there, and it flows back and kind of impinges on the back, and then as it distributes through the rest of the motor compartment, gets heated up and ultimately exits out that fan that's pulling air out of the system. If you want to look at that parameter more three-dimensionally, you can go and look at surface plots. And so in this case, we've selected two parts. We've selected the enclosure, and you can see, by the way, by shrinking down that computational domain, it is just modeling this portion of the assembly. So you see the enclosure as well as the motor. Obviously, the motor is the hottest device in here. But even you can see the impact of the temperature on the plastic as well, which you may have a concern if you're designing this also. Lastly, in terms of visualizing, we would go to flow trajectories, which is kind of a nice way to more three-dimensionally see what's going on with the flow. So let's go ahead and play those. So this animation here shows you what the flow field looks like within this device. And again, this is one of the big benefits of CFD. And it's a thing that's hard to get experimentally, right? You may set up your test rig, thermocouple it everywhere, but still kind of connecting the dots as to why you're getting what you're getting. CFD really helps you visualize that. And so if we look at our problem, just to understand this flow field, the flow kind of comes in from that inlet, and it has enough momentum that it goes to that back wall, impinges, and sort of spreads out throughout the compartment there, which is good, although there's a decent portion that looks like it sort of stays low and then heads out and leaves through our fan. So that whole amount of the flow really probably isn't doing much of a job with respect to cooling. So the engineer, having seen this, might say, well, I'd like to maybe reposition those vents, those ducts, to maybe get more flow induced across the motor and maybe cool it a bit more effectively. And again, this is where the power of working in solid edge comes in. What we can do is make use of the family of assemblies in solid edge to manage different cases that we want to run in this same assembly. So what we've done is I've moved to a new configuration here, and you see that fan outlet has been moved up to the upper right-hand corner. And to do that, that was really easy to do. Just use the synchronous technology in solid edge once I created that new member and just dragged it right up to that upper right-hand corner. And then to get all of the CFD information to that new case, all I have to do is go and clone the project. So I take my first case that I set up through the wizard and the rest of the tree, and then clone it to that new geometry that I want to test. So really, in the matter of a few minutes, I could be running my next case. And so if we look at that second example and just briefly show the surface plot. So now we're looking at the temperature again, and it's on the same scale as the previous one, so you can see that the motor is a bit cooler than in our first example. And if we go back to the flow trajectories, just because everybody likes to see flow trajectories, we'll go ahead and show those for our second case as well. And you can see what that new flow field looks like. And one thing, as I set this thing up and ran it, if I look at it from a little bit from the front again, there is still flow that goes along the floor, as in the first case. But then after that, it still has to be dragged up past the motor on the right-hand side there to get to the fan exit. And I think in doing so, that's what's able to take more heat off of that motor, and it's what brings down the temperature of it in this second case. So with that, I'll go ahead and move back to our slideshow just to sort of finish up and summarize some of the things that we've seen. A couple of the tools that we won't have a chance to get to in the live demonstration. One is the compare tool, and this is a convenient way to go ahead and take the two designs, put them next to each other, and really see the differences visually. You can see, of course, that second case is cooler, although the plastic around it looks like it is a little bit warmer. So as an engineer, you may decide, well, is that an impact that I can deal with, or is it something I need to consider? But again, that's the power of doing CFD, is seeing these different things. From there, if you set up several of these cases, you can manage all of them through our batch run facility, including farming them out to different computers on your system. And then use things like parametric study, optimization, design of experiments, including even being able to tie in an external optimizer to link into your CFD solution. So lots of ways to, in a more automated way, run FloEFD and help you arrive at that best design.